So this is Lecture 3, Part 4. Today we're going to talk about derivatives of compositions of functions. This is often known as the chain rule. So I should say Lecture 3, Part 4, derivatives of compositions of functions, also known as the chain rule. And this is the part of differentiation that oftentimes gives students a bit of grief, but I think if you work enough examples and understand the techniques via this lecture, we should be able to get through it just fine. Okay, so what is the chain rule? Well, it goes as follows. Suppose we're given two functions, two differentiable functions. Let's see here. Let me pull up a note here. 1 second. Let me grab my notebook. So if f and g are two differentiable functions, we have the following results. Turn to the page, and I'm referring to the lecture notes that are online. So if g is differentiable, and f is differentiable that is, f is differentiable at g of x, then the composition of f composed with g, okay, so we'll let uppercase f equal to the composition of the two functions, f composed with g, which of course is equal to f of x, big F of x, which is also equal to f of g of x, is, okay, so f of x is differentiable at x. Okay, and so what do we mean by differentiable at x? That means if we pick a point P on the function big F with abscissa equal to x, then we can calculate the slope of a tangent line at x. Okay, that's all that means. So, and so if f is differentiable at x, what do we have? Okay, so what would its derivative be? So here's the formula. F prime of x is equal to the derivative of little f of x, okay, evaluated at g of x, times the derivative of g. Right? So this is the important formula. Now, I'm not going to prove this. There is a proof of this formula in the lecture notes. It's a little bit complicated. It involves manipulation of some epsilon delta structures, and I think you guys had enough of this from Chapter 2. So we're just going to make use of this formula, but it's a very important formula. for the rest of the class. So I'll work through some examples, and if you have any questions about that, please let me know. And if you're spending a lot of time trying to calculate derivatives of compositions of functions, get with me and I can show you some simple ways of managing this. So in other words, if we have something like this, one way of visualizing the derivative of a composition of functions, suppose that I have y is a function of u, okay? And u is equal to a function of x. All right, suppose I have these arrangements. Now I want to calculate from these two pieces of information, I want to extract out the derivative of y with respect to x. Now I'm going to give you what engineers use, but not what typically mathematicians use. But it still works for the most part if you're a math major, so you shouldn't have to worry about it too much. But one of the things we do is we can do essentially what's called a separation of differentials. In other words, since y is a function of u, go ahead and differentiate y with respect to u, and then multiply that derivative by the derivative of u with respect to x. Okay? And you get this kind of semblance, but it's not mathematically correct, of a cancellation of these differentials. But that's not mathematically what's going on, but mathematically it does work quite often. Okay? And for this class, it will work for the problems that we have. So for instance, why is this important? Well, suppose I ask you to calculate the derivative with respect to x of this function. Okay? And clearly, if you did your Chapter 1 homework, you can recognize at the outset that this is a function g of x, which is equal to x squared plus 1. And then if we let f equal to a square root function, and then g equal to x squared plus 1, then we can see that this function is f composed with g. All right, so you should be able to discern that readily. So now the way we will calculate its derivative is, say, suppose we let u equal to x squared plus 1, like so. All right, and then we let y equal to the square root of u. And so we can use then this result that I'm circling in green. Use this result. Okay, so differential y over differential x is equal to differential y with respect to u times differential u with respect to x. Okay, so, and now we have u and y defined, so we just go ahead and make the calculations. So what is dy over du? Differential of y over differential u, okay, we use this formula right here, that would be 1/2 u to the minus 1/2, okay? And what is du over dx? So du over dx is equal to 2x, okay? And so now to get the complete derivative, we just multiply the two quantities together, and so we have f prime of x okay, that would equal to 1/2 u to the negative 1/2 times 2x. Now we want this result expressed in terms of x, so we substitute in what u is in terms of x. So here we have, right here, u is equal to x squared plus 1. So we plug that in for u. So we have 1/2 times u, which is x squared plus 1, to the negative 1/2 times 2x, and then we can simplify that. So the answer will be x divided by the square root of x squared plus 1. All right, so for that example. All right, so, okay. So we'll just work through a number of examples. Next page. So how about we calculate the derivative of this function? Y is equal to the sine of x squared. Okay, so again, we have y is equal to the sine of u, and then we let u is equal to x squared. And so the derivative, y prime, would equal to the derivative of sine u with respect to u times the derivative of u with respect to x. Okay? And so when we perform this calculation, we'll have, well, we know the derivative of sine function is the cosine, so y prime is equal to the cosine of u, and du over dx is 2x. And now we just plug in our value for u, and so we get cosine x squared times 2x. And don't forget the meaning of a derivative. It's the slope of the tangent line to this graph at some particular value of x. Okay. So how about we take a variant of this problem? How about y is equal to sine squared x? Okay. One of the things we can do is we can use what's called the power rule of differentiation for functions. So if we have, I'll write it in green, if we have a function, say, y is equal to f squared of x, and assuming that f is differentiable, then y prime, since we have a power, we can treat it just like any other exponent differentiating with respect to any other exponential function. We can say that y prime is equal to 2 times f of x times f prime of x. Okay? Because what we're doing is we're letting f of x equal to u. So this is called the power rule for differentiation. So in this case, for y is equal to sine squared of x, we can just say, we can treat the sine function just like any other function. This would be 2 times sine x times the derivative of sine x, which is cosine x, which, if you're familiar with your trig identities, this is simply the sine of 2x. All right. Okay, so let me give you a generalized rule for the derivative of a function raised to a power, and this will be called the power rule for differentiation. So we know if we have something like this, the derivative with respect to x of, let me see here, say u to the n. Okay? Well, we differentiate it just like we would do any other variable. This would be, say, if we would differentiate this as if u were equal to x. So you recall the derivative with respect to x of x to the n is equal to n times x to the n minus 1. Right? Now, if u is, say, some function of x, okay? Suppose we let u equal to some function of x. Now here, I'm going to differentiate, so let's come back here, okay? And we let, suppose our function is equal to u to the n. So then, in this case, the derivative with respect to x of u to the n would be, that would equal to n times u to the n minus 1, and now we invoke the chain rule times the derivative of u with respect to x. Okay, so this is the power rule for differentiation. So, for instance, if I give you, say, the derivative with respect to x of g of x to the n. So this would be n times g of x to the n minus 1 power times g prime of x. And you can also, something else, you can also note that, as an aside, when we take the derivative of with respect to x of, say, x to the n, we're actually using the chain rule as well in some respects. Okay, we can actually write it this way if you want to be consistent. And of course, you recognize that this quantity is simply 1, so it's just, it really essentially goes away. But in the case of where the function, instead of x, you have a function, say g of x, okay, then you'll have to multiply the derivative by the resulting calculation by g prime of x, and this is the chain rule. This is the chain rule, a very important concept in calculus. Okay, and so I can't emphasize how important this is. So let me show you the utility of using the chain rule. So from here out, we'll just do a fair number of examples. Okay. So how about we let's say define this function. G of t is equal to a rational function, say t minus 2 divided by 2t plus 1. Okay, and we raise it to the 9th power. And so we want to calculate g prime of t, which is equal to the derivative of g with respect to t, written this way. Okay, so using the previous formula, we'll get that g prime is equal to 9 times the function in brackets raised to the 8th power, and then we multiply that result by the derivative with respect to t of the composed function, the inner composed function, which is 2t plus 1. Right? And so now we can simplify. So that would equal to 9 times t minus 2 divided by 2t plus 1 to the 8th, okay, times, okay, so now we have to use the derivative of a quotient, right? We have to use the quotient rule for differentiation. So that would be the bottom function times the, there's a plus there, 2t plus 1 times the derivative of the top, which is just 1, minus the top function, which is t minus 2 times the derivative of the bottom function, all divided by the bottom function squared. Okay. And if you want, okay, and so we could simplify the numerator of this rational part right here. I'll leave it to you as an exercise to simplify this piece. So you can investigate simplifying this. Well, let's see, should I go ahead and do it? Why don't I go ahead and complete it? I'll go ahead and complete it for you. It looks a little bit involved. So let me complete the simplification. So I won't leave it to you, I'll do it for you. So that would be 9 times t minus 2 divided by 2t plus 1 to the 8th. And so we're left in the numerator here of, what is that? That's 2t minus 2t, so that would cancel. And so this would be 1 plus 4, so that appears to be 5, right? 5 over 2t plus 1 squared. Okay, and we can simplify it even further. That would be 45, because 9 times 5 is 45, times t minus 2 quantity to the 8th power all that divided by what? 2t plus 1 to the 10th, because I'll add the exponents in the denominator. Okay, so that would be the simplification of that rational expression. All right, so let's do another one. Next page. How about we calculate the derivative of this function? 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. So in this case, we have a product of two functions. So if we call this factor u, and if we call this factor v, we'll have to use the product rule for differentiation. And so y prime is equal to u times the derivative of v with respect to x plus the derivative of u with respect to x times v. Okay, so what is dv over dx? Well, v is equal to x cubed minus x plus 1 to the 4th. So now we have to use the power rule for differentiation. So v prime, which is dv over dx, that would equal to 4 times x cubed minus x plus 1 cubed times the derivative of what's inside of the parentheses, 3x squared minus 1. See, we have to take the derivative of the guts of the function, so to speak. Okay, so that's v prime. And now we have to calculate u prime. So u is equal to what? 2x plus 1 to the 5th. 2x plus 1 to the 5th. So u prime then would equal to 5 times 2x plus 1 to the 4th times 2. Okay, and we can multiply the coefficients. 10, 2x plus 1 to the 4th. And so now all we do is we plug in the quantities into the derivative formula. All right, so we get y prime is equal to u, which is 2x plus 1 to the 5th times dv over dx, which is 4 times x cubed minus x plus 1 quantity cubed times 3x squared minus 1. Okay, and then we have to add to that du over dx, which we said was 10 times 2x plus 1 to the 4th times v, which is x cubed minus x plus 1 to the 4th. Okay, and good luck trying to simplify this. You may leave this expressed like this. All right, so do I have some more examples? I probably do. Oh, okay. And so with the chain rule, we have a simpler derivation for the proof for the derivative of an exponential function. So let me show you a simplified approach. Remember when we calculated the derivative of an exponential function, we had to go through a rather arduous tabular approach, and then I kind of gave to you that the coefficient of the derivative of an exponential function was the natural log of the base. Well, here's the justification for it. Now that we have access to the chain rule, the calculation of this derivative becomes easier. Right? So recall that we can reformulate a to the x in terms of an exponential. Okay. Now, why is this true? We know that e to the x and the natural log function, ln x, are inverses. Okay, and we know that a function composed with its inverse is equal to the argument of the function. Okay, so with this in mind, we know that e raised to the power of natural log of x is the same as e to the x composed with the natural log of x, which is equal to x. Okay, so knowing that, we have a to the x can be written as e to the natural log of a to the x. Okay, and so why do we want to know that? All right, so we know this. Okay, so let me show you how we can use that to solve this derivative in an easy way. So with that in mind, the derivative of, with respect to x of the exponential function can be written as the derivative with respect to x of e to the natural log of a to the x. And now we know that the natural log of a number of a variable raised to a power can be written using logarithmic expansion. So the exponent becomes a coefficient. So we have something like this. Okay, by the rules of the expansion of the logarithmic functions. Okay, so now all we have to do at this level is apply the chain rule. So we take the derivative of the exponential function. Recall that the derivative with respect to x of e to the x was e to the x. Okay, we demonstrated that. Now, the derivative with respect to x of e, if we replace x with a function of x, okay, the chain rule stipulates that this will be the function itself times the derivative with respect to x of the function. This is the chain rule. All right, so now in this case we're pursuing the derivative with respect to x of e to the natural log of a times x. So this is essentially your f of x. Okay, and so if we do the calculation, this would equal to the function itself times the derivative with respect to x of the function of the, it's in the exponent. So the derivative with respect to x of the natural log of a times x. Right? And so e to the natural log, okay, so we'll go ahead and put back, we'll do a contraction of this piece right here. We'll go ahead and do a logarithmic contraction there. So we'll put it back, so this would be e to the natural log of a to the x. And this number right here, natural log of a, that's just a number. So that comes out of the derivative calculation. All right? And so we're left with the derivative with respect to x of x, which is just 1. Okay, and so now we can write this, the natural log of a, and since e to the natural log of a number is just the number itself, we have this. And so there's your formula for the derivative of an exponential function. Okay, so that's the proof. A simpler proof than having to use a tabular approach. All right. Okay, so in this I expect you to memorize and also understand the proof of this, right? Okay, so can we do some more examples? Sure, let's do some more examples. How about we calculate the derivative of, say, y is equal to 10 raised to the 1 minus x squared power. Okay, something you may have seen in algebra. So we want the derivative of this. So we know that the formula for the derivative of an exponential function is simply it'll be the function itself. So in this case, it'll be the function itself times the derivative with respect to x of the exponent times the natural log of the base. Okay, so now we coalesce all of these terms. So this would be 10 raised to the power of 1 minus x squared times a negative 2x times the natural log of 10. Right, and so, yeah, so you can leave the answer like that. Okay, what else? How about something like y is equal to e to the x? Okay, so we want to calculate its derivative. So according to the formula, it will be the function itself times the natural log of the base times the derivative with respect to x of the exponent. Okay, and so this would be e to the x. Now the natural log of e is 1, and the derivative with respect to x is e to the x. And so we can write it as e to the x plus x. Okay, so that would be the solution there. How about this? Say y is equal to the tangent of the tangent of the tangent of x. Now I'm not sure of I can't think of any particular application of this function, but nevertheless it does have a derivative, okay? And so y prime would equal to the derivative of the outer function, which would be, okay, so the derivative, all right, so it would be, how you would solve it is you would go like this. You would take the derivative of the outer function, which is here. So the derivative of the tan function is secant squared, okay, and then you plug back in its argument. Okay, and then of course you have to apply the chain rule component. So you'd have to take the derivative with respect to x of this piece right here. Okay. Okay, and now we have to clean up the derivative. So that would equal to secant squared times the tangent of x. Okay, times, okay, so now we take the derivative of this piece right here, so that would be secant squared of the tangent of x. Okay, and then we have to take the derivative of the argument to this piece. So we have to take this derivative, and so that would be times the derivative with respect to x of tan x. Okay, so we're almost done. So now the answer is the secant squared of the tangent of x times secant squared of the tangent of x times, okay, the derivative of the tan function is just secant squared of x. Okay, so that's the derivative of the tan of tan x. Okay, all right, so it's that big long formula. Interesting. All right, so how about consider this function. Y is equal to x times sine of 1 over x, and we want to calculate its derivative with respect to x. So we'll have to use the product rule for differentiation. Okay, so y prime is equal to x times the derivative with respect to x of sine of 1 over x plus sine of 1 over x. Well, I guess I need to be explicit here. Okay, so plus the derivative with respect to x of x, right, because right there, times sine of 1 over x. Okay, and you know that just becomes 1. Okay, so thus we have, so the derivative with respect to x of sine 1 over x, that would be the derivative of the outer function, which is cosine. So that would be cosine of 1 over x. Okay, and then by the chain rule, we have to take the derivative of the argument to the sine function, like so. And then we finish it off. Okay, and so now we just clean up the remaining derivatives. So this would equal to x times the cosine of 1 over x. Okay, and the derivative of 1 over x, as we've noted before, that would be minus 1 times x to the minus 2 plus sine of 1 over x. And then we can simplify this, so this would be minus cosine of 1 over x times 1 over x plus sine 1 over x. Okay, all right. So one more example, well, a couple more examples. How about we calculate the derivative with respect to t of this function. T divided by t squared plus 4. Okay, so you can see that the outer function is the square root function, and the inner function is that rational function. Okay, so I'll circle in blue the inner function. Okay, all right. So in this case, what would probably be a useful technique is if we let, say, f of u equal to the square root of u, and if we let u equal the function of t. Okay, if we recognize the pieces of the composition, so then we can say that the derivative of f is equal to the derivative of f with respect to u times the derivative of u with respect to t. So we can use that alternative form of the chain rule. That might be helpful to visualize it. So the derivative of f with respect to u is nothing more than 1/2 the derivative of the square root function. So 1/2 u to the minus 1/2. And then the derivative of u with respect to t, well, we have to use the quotient rule for differentiation. So that would be the bottom function times the derivative with respect to t of the top. So that would be dt over dt minus the top function times the derivative with respect to t of the bottom, all over the bottom squared. Okay, and so we can write 1/2 u to the minus 1/2. Okay, and that would be what, t squared. Simplifying the numerator algebraically, that would be minus t squared plus 4, right? Over t squared plus 4. All right, and all we have to do next is just plug in the value of u. So this would be 1/2 And u is what? T over t squared plus 4. Okay, and all of this to the, I forgot to square that, didn't I? Sorry, I need to square this. The bottom squared, right? Okay, make that correction. Okay, so it would be, okay, so we have right there, and then times what? Negative t squared plus 4 over t squared plus 4 squared, okay, which is equal to 1/2 times t squared plus 4 to the 1/2 over t to the 1/2 times a negative t squared plus 4 over t squared plus 4 squared. Okay, all I did was I took the reciprocal and raised the numerator and denominator to the 1/2 power, and then we can simplify the exponents. So this term will cancel, and then this exponent becomes what? 2 minus 1/2, which is 3/2. Okay, so if you just simplify that, and that's 1/2 too, right there. All right, so there's your answer for that. All right, what else can we do? Okay. Find an equation of the tangent line to the curve at a given point, at the given point. So if we have y equals sine x plus sine squared x, and we want to find the equation to the tangent line to this function at, say, the origin, 0, 0. Okay, so the equation then would be y is equal to mx. So all we have to do is find m. So m, the slope of the tangent line, is equal to the derivative of the function. So that would be, the derivative of this function would be cosine x, right? Take the derivative of that term, and then plus 2 sine x times cosine x. Okay, because that would be the derivative of that term. And then we evaluate it at x equals 0. Okay, so m is equal to 1. So y equals x is the equation of the tangent line to this graph at the origin. All right, so anything else? All right, so that concludes section 3.4 lecture notes. So I highly encourage you to get started with your WebAssign as soon as possible and start looking at your project number 3 for this chapter. And again, if you have any questions, please contact me. The Chapter 3 Part 1 exam will be on the first 6 sections of Chapter 3. So we have 2 more sections to go, 2 more lectures to go before we have our Chapter 3 Part 1 test. So please stay current in your studies of this chapter. It's a very important chapter. Okay.